Welcome to this explainer. Okay, today I am literally so excited to decode the invisible mechanics governing the everyday objects right in front of us. Have you ever just stopped, stared at something swinging back and forth, and realized, wow, there is a profound, completely hidden rhythm to this? Well, we're going to uncover exactly that. We're diving into the fascinating mathematical heartbeat of the universe, something we call simple harmonic motion. Let's get right into it.
So here's our mental roadmap for this explainer. We'll start with the rhythm of time, then defining simple harmonic motion, check out velocity and acceleration, look at the energy dance, and finally, bring it all home with this simple pendulum.
All right, jumping right into part one, the rhythm of time, grounding the physics.
Before we hit the heavy math, we really need to anchor our understanding in reality. Take a look at the simple, elegant swing of a classic grandfather clock. It absolutely perfectly illustrates what physicists call oscillatory motion. Think about it for a second. The pendulum swings back and forth repeatedly around a fixed point. It happens over and over in a very definite, reliable interval of time. It barely seems to move, right? Yet it keeps remarkable accuracy day in and day out, totally confined within these well-defined limits.
Which brings us to Section 2, defining simple harmonic motion, the language of oscillations.
Okay, to really grasp the hidden rules of this universe, we've got to get our jargon straight first. First up is the time period. You can think of this as the fundamental beat of our physical dance. Strictly speaking, it's defined as the least interval of time after which a body's periodic motion completely repeats itself. And naturally, the standard everyday unit we use to measure this beat? The good old second.
Right after that, we have frequency. Now, if the time period is how long one single dance takes, frequency is how many of those full back-and-forth motions happen in just one single second. We measure this in hertz. So picture a pendulum swinging back and forth a complete 2 times in 1 second. Boom! Its frequency is exactly 2 hertz. Simple as that.
Then there's phase. And phase is absolutely crucial because it tells us exactly where our object is in its choreographed routine relative to its mean position. At any exact instant, the phase expresses the complete position and the specific direction of motion for our vibrating particle. It's basically the GPS for our oscillator.
Now here's a huge distinction we need to make, the difference between pure harmonic oscillation and non-harmonic oscillation. Pure simple harmonic motion is just beautiful in its simplicity. Why? Because it can be expressed mathematically by a single harmonic function, like a pure sine or cosine wave. Non-harmonic oscillation, on the other hand, is kind of messy. It's a complex combination of 2 or more harmonic oscillations all mixed together. You can't just sum it up with one single function.
Moving right along to Section 3, velocity and acceleration, the microscopic dance.
Let's actually see how this all builds into this microscopic dance between displacement, velocity, and acceleration. If you look closely at these 3 graphs representing them, you'll spot something wild. Notice how velocity is actually ahead of displacement by a phase angle of exactly 90 degrees. And then check out the acceleration curve. It's a full 180 degrees ahead, literally totally opposite to displacement. So they're all following the exact same underlying rhythm, but they hit their peaks and valleys at completely different times in the choreography.
And this table right here perfectly summarizes that timing. Picture yourself on a playground swing. When that swing goes as high as it can possibly go in the air, that extreme edge, your displacement is at its absolute maximum. But for just a split second, you stop entirely. The velocity is 0. But here's the crazy part. At that exact motionless moment, the acceleration pulling you back down is at its absolute maximum. On the flip side, when you're zooming right through the middle, the equilibrium position, your displacement and acceleration drop to 0, but your velocity, completely maxed out.
So, seeing all of this perfectly balanced, almost magical mathematical choreography really begs the question, what actually fuels this? What invisible forces are shuttling this pendulum back and forth endlessly without ever breaking the rhythm?
That brings us to Section 4, the energy dance, potential versus kinetic. Let's take a look at the core engine of our system, which is basically a continuous, endless transfer of energy. It's so cool how these 2 forms of energy trade places. Potential energy hits its absolute maximum at the extreme positions, like when our swinging object is pulled all the way back and then drops to completely 0 right at the mean equilibrium position in the middle. Kinetic energy does the exact opposite. It hits maximum as the object rushes rapidly through the center and falls to 0 at the extreme edges. The energy is just constantly shuttling back and forth.
Now, what's really mind-blowing is how perfectly these forces balance each other out. If you look at the curve for potential energy, marked U, and the curve for kinetic energy, marked K, you see them intersecting. They're constantly fluctuating, kind of like a seesaw. But look at that top line representing total mechanical energy, marked E. It remains a completely flat, unchanging horizontal line. The energy is simply changing forms. The total amount never ever changes. It's perfectly conserved.
And our final stop, Section 5, the simple pendulum, math in the real world.
Let's zoom back out from all that microscopic math and apply these rules to something tangible. Using the simple pendulum as our main protagonist again, we can clearly see the real-world forces at play. When the bob is displaced by a small angle, just look at the vectors in this diagram. Gravity steps up as the essential restoring force. Specifically, it's that one component pulling the bob back down toward the center that keeps this entire simple harmonic motion going.
And this leads us to some pretty incredible conclusions. As we just saw, the restoring force is provided by gravity. But take a look at the time period formula here. T equals 2 pi times the square root of L over G. I really want to emphasize a totally surprising fact about this. The math proves that a pendulum's rhythm doesn't care at all how heavy the bob is. The period is completely 100% independent of the mass. The time it takes for a full swing relies solely on the string's effective length and the planet's gravitational pull. How crazy is that?
I think this brings our explainer full circle beautifully. To quote the text directly, the elegance and simplicity of this oscillator suggest that there is little to go wrong with it. The oscillatory energy and the forces that shuttle it between its potential and kinetic forms are provided by gravity. Honestly, it is deeply fascinating how these dense, complex trigonometric equations ultimately describe something so profoundly elegant, stable, and fundamentally simple.
Which leaves us with this final thought for you to chew on. If these incredibly simple mathematical rules perfectly govern the majestic swing of a clock, what other complex rhythms of the universe are just waiting out there to be decoded? Thank you so much for joining me on this explainer to uncover the math hiding in plain sight. Keep looking for those invisible rhythms out there,